Hello everyone, here is Khaled Omar, and in this video I'm going to demonstrate Chapter 3 of the CCNA 200-301 Volume 1, which is Fundamentals of WANs and IP Routing. The contents of this video will discuss two main topics. The first will be Wide Area Networks or WANs, and the second topic will be IP Routing. So let's start with Wide Area Networks or WANs. To remind you, we discussed Ethernet LANs in the second video, Chapter 2, and in this video we are going to discuss Wide Area Networks. And we defined LANs and WANs and in the first video as LANs, local area networks or networks between nearby devices, and wide area networks or WANs are networks between devices that are far apart. So let me bring the highlighter or the pen. WAN technologies defines the physical layer, layer 1, standards, and the data link layer, layer 2, protocols, which used to communicate long distances. So in this presentation we will discuss two main technologies for WAN, which is leased line WANs and Ethernet WANs. Let's start with leased line WANs. To connect LANs using a wide area network or WAN, the internetwork uses a router connected to each LAN. Let's assume we have here local area network 1, and let's assume we have here local area network 2. We need connectivity, or we need to connect these two LANs who are far apart with a long distance, and each LAN is connected to a router that resides on each LAN. So we are going to use wide area network to connect these two LANs, and the type of WAN that we are going to use will be leased line. So a router at each site connects to both the WAN link and the LAN. This is how the WAN will be accomplished. But as you can see here, a leased line is connecting the two routers. So in fact, this leased line looks like a cable between the two routers. So in this slide, we are going to discuss the physical details of the leased lines. The leased line service delivers bits in both directions for transmitting and receiving at a predetermined speed using full duplex logic. And we discussed and defined what is full duplex in the chapter 2, to send and receive simultaneously. In fact, it acts as if you had a full duplex crossover Ethernet link between the two routers. As we mentioned, when you are going to connect two same devices, you should use crossover cable. So in fact, the link looks like a crossover Ethernet link between the two routers, like that. The TX here is connected to the RX here, and the TX here is connected to the RX here. So transmit pair is connected to the receiving pair on the other side, and the receiving pair is connected to the transmitting pair on the other side. So the leased line uses two pairs of wires, one pair for each direction of sending data, which allows full duplex operation. So in this figure, we have here LAN 1, that consists of several number of switches that connects hosts. We have here many hosts connected to switch 11 and another hosts connected to switch 12. And eventually we need this to connect this LAN to another LAN in another building, building 2, which contains hosts that are connected to switch 21 and hosts connected to switch 22. So we will use a router on each site, and we will connect these routers using a leased line that can support long distances, and in this example support up to 1,000 miles. Actually, leased lines have many differences compared to an Ethernet crossover cable. To create such possibly long links or circuits, a leased line does not actually exist as a single long cable between the two sites. Instead of that, the telephone company or the central office that creates the leased line installs a large network of cables and specialized switching devices to create its own computer network. The telco or the telephone company network creates a service that acts like a crossover cable between 2 points, but the physical reality is hidden from the customer. So let's define the term leased line. It refers to the fact that the company using the leased line does not own the line, but instead pays a monthly lease fee to use it. Because none of the companies have the rights to dig in the streets and put cables, except some companies or the telephone companies that has the authority to run cables under the streets and give the companies the fee, the monthly or annual fees to lease this leased line. That's why it's called leased line. This table lists some of the different names for leased lines. Sometimes we call it leased circuit, sometimes we call it serial link, sometimes we call it point-to-point link, T1 link, or private link. Each name of these has a specific meaning. Like for example, leased circuits. The word circuit are often used in telco terminology. So when you find any of these names, they are all referred to the leased line. Let's give the meaning of the serial link. Serial refers to the fact that the bits flow serially, and that routers use serial interfaces. Point-to-point link. These terms refer to the fact that the topology stretches between 2 points and 2 points only. Point to point, not point to multi-point. We call point-to-point link between 2 points only, like that. T1, this specific type of leased line transmits data at 1.544 megabit per second. So this is a standard. When you hear about T1, remember that the speed of transmitting data will be 1.544 megabit per second. The name private line, this term refers to the fact that the data sent over the line cannot be copied by other telco customers, so the data is completely private. To create a leased line, some physical path must exist between the two routers on the ends of the link. The physical cabling must leave the customer building where each router sits. However, the telco does not simply install one cable between the two buildings. There is no one cable between the two buildings. But actually, instead of that, it uses what is typically large and complex network that creates the appearance of a cable between the two routers. Let's look in this figure. Telephone company 1 has a switch 1 and telephone company 2 has switch 2. And the two routers at the customer sites, site 1 is connected to switch 1 and switch 1 is connected to switch 2. All these cables are underground and switch 2 is connected to router 2. But the eventual diagram or the eventual figure will look like a leased line between the two routers. But the actual figure is the routers are connected through telephone company switches. A leased line provides a layer 1 service, and this layer 1 defines the physical layer on the TCP/IP. As we mentioned in the TCP/IP model, that layer 1 is the physical layer. The leased line itself does not define a data link layer protocol because data link layer protocol is layer 2 to be used on the leased line. Because leased line define only the layer 2 transmission service, many companies and standards organizations have created data link protocols to control and use leased lines. Today, the two most popular data link layer protocols used for leased lines between two routers are HDLC or High Level Data Link Control Protocol and the point-to-point protocol. These two protocols are layer 2 or data link layer 2 protocols. All data link protocols perform a similar rule to control the correct delivery of data over a physical link of a particular type. When we have a router here and a router here and we have a leased line between these two routers, we must use a layer 2 protocol, one of these two, HDLC or point-to-point protocol. Why? To control the correct delivery of bits or data over this physical link. Let's start by the first type of the layer 2 data link protocol, which is HDLC, data link frame format fields. The frame format consists of a flag, address, of course the destination address, control, and by the way, 1 byte for flag, 1 byte for address, 1 byte for control, 2 bytes for type, and here is the data that comes from the upper layer, and we have a trailer of 2 bytes frame check sequence. This is the HDLC frame format. You have to keep it in your mind and remember that it is used to control the successful delivery of bits between two endpoints. Let's take the first field, which is flag. Its equivalent on Ethernet is the preamble or the start of frame delimiter. It lists a recognizable bit pattern so that the receiving nodes realize that a new frame is arriving, because we have a stream of data 1 0 1 1 1 0 1, a stream of data, and so on. So which bit or which flag determines the start of frame and the end of frame? The flag is doing this purpose. It says that this is the start of a new frame. So when a lot of bits of stream of data is coming between two endpoints, the flag identifies that the receiving node can know the start of the frame. The second field is the address, which is equivalent to the destination MAC address on the Ethernet. It identifies the destination device. The control byte has no equivalent on the Ethernet, but it does here for the purpose which is mostly used for purposes no longer in use today for links between routers. Actually, it is not used today for the links between routers. The type field, which is 2 bytes, it's equivalent to the type field represented in the Ethernet frame format. And the description, it identifies the type of layer 3 packet encapsulated inside the frame, whether the packet is an IPv4 or an IPv6. The trailer or the 2 bytes field, the frame check sequence, it's equivalent to frame check sequence on the Ethernet, and it is used for error detection per process. And we describe the function of the frame check sequence to when a receiving node receives a streams of bits, it can use the trailer bits to determine whether an error occurred or not. So it's used for the error detection purposes. So let's discuss here how routers use a WAN data link from the router's perspective. Let's assume we have here LAN 1 and we have here LAN 2. Each LAN is connected to a router, and the router is connected through a WAN leased line link, and PC1 needs to communicate to PC2. First of all, PC1 recognizes that PC2 is not on the same network, and we will discuss in the IP routing section what it means. The destination is not in the IP network. PC1 realized that PC2 is not in the same network, so it decides to send the frame to R1, the default gateway or the default router in the LAN 1. Router 1 first, it removes the Ethernet header and trailer used by PC1 and encapsulate a new header and trailer based on the WAN, the layer 2 data link layer protocol used between router 1 and router 2. If it's an HDLC, it will encapsulate this frame, header and trailer, to the IP packet and send to R2. Then R2 receives an HDLC frame that contains header and trailer, and it removes the header and trailer and with a process called de-encapsulation of removing the HDLC header and trailer, and based on the destination network, the network where the destination host resides, R2 will re-encapsulate a new header and trailer and send the frame to BC2. As we mentioned, BC1 sends a frame with an Ethernet header and trailer to R1. Step 2, R1 de-encapsulate or removes the Ethernet header and trailer and before sending to R2, it re-encapsulates a new header and trailer based on the protocol used between R1 and R2 and re-encapsulate this header and trailer inside the packet, re-encapsulate the IP packet inside a new header and trailer, HDLC header and trailer, of course, because the layer 2 protocol used here is HDLC, not point-to-point, and send the frame to R2. Then R2 decides that the destination is on LAN 2, which is an Ethernet network. So it de-encapsulates the HDLC header and trailer and re-encapsulates a new Ethernet header and trailer and send the frame to BC2. Why routers do this process? Because let's assume in this side the switch received an Ethernet frame. Based on the contents of this Ethernet header, the switch can take decision and forward the packet successfully to BC2. But here, to deliver the packet successfully, we use another data link layer 2 protocol. That's why routers keep doing de-encapsulation for the Ethernet header and trailer and re-encapsulate a new header and trailer to deliver the bits successfully either over the LAN network or the WAN network. Second, let's discuss Ethernet WANs. We discussed now leased lines, and now we are going to discuss type 2 of the wide area networks, which is Ethernet WANs. Actually, for the first several decades of the existence of Ethernet was only appropriate for LAN, and remember that it was. The restrictions on cable lengths and devices might allow a LAN that stretched a kilometer or two to support a campus LAN, but that was the limit. As time passed, the IEEE improved Ethernet standards in ways that made Ethernet a reasonable WAN technology. For example, the 1000 base LX standard uses single-mode fiber cabling with support for a 5-kilometer cable length, and the other standard 1000 base ZX standard supports an even longer 70-kilometer cable length. As time went by, and as the IEEE improved cabling distances for fiber Ethernet links, Ethernet became a reasonable WAN technology. Today, many WAN service providers offer WAN services that take advantage of Ethernet. Service providers offer a wide variety of these Ethernet WAN services with many different names. Actually, if you have a router here connected to a LAN, let's call it LAN 1, and another site connected to LAN 2, and we want to use a WAN type to connect these two LANs so they can communicate with each other. All you have to do is to connect a physical cable, fiber cable, between router 1 and the service provider switch. We call it service provider point of presence. And similarly on the other side, connect router 2 through a fiber cable with a fiber cable connected to service provider 2 switch or the point of presence, and the Ethernet WAN service of the service provider here will deliver the packets successfully between the two endpoints. So the router is called the customer premises equipment because it's related to the customer, and the switch is called service provider point of presence. One moment. The customer connects to an Ethernet link using a router interface, and the fiber Ethernet link leaves the customer building and connects to some nearby service provider location called a point of presence. Instead of a telco switch as shown in the figure 3-3, which you are connected through a physical link to service provider switch 1 and then telephone company switch 2 and then to the router on the other side. And instead of that, the service provider uses an Ethernet switch. So instead of this telco switch, we use an Ethernet switch on both ends. And using the service provider network, we can have a WAN technology that guarantees the successful delivery of bits between the two routers and connect the two LANs to each other. Inside the service provider's network, the service provider uses any technology that it wants to create the specific Ethernet WAN services. Inside this provider network, we can use any type of technology that can successfully deliver the packets between the two endpoints. So for Ethernet WANs, if you can imagine two routers with a single Ethernet link between the two routers, you understand what Ethernet over MPLS service does, as shown in the following figure. In this case, the two routers R1 and R2 connect with an Ethernet over MPLS service instead of a serial link. The routers use Ethernet interfaces, not serial interfaces, like in case of leased lines. And they can send data in both directions at the same time. Physically, each router connects to some service provider point of presence, as shown in the previous figure, but logically, the two routers can send Ethernet frames to each other over the link, not HDLC frames like in leased lines. So when router 1 here will receive an Ethernet frame, it will de-encapsulate the Ethernet frame and re-encapsulate a new Ethernet frame before sending to R2. And similarly, R2 will de-encapsulate the WAN Ethernet frame and re-encapsulate another Ethernet frame to send to PC2. Actually, we almost said this in the previous slide, The Ethernet over MPLS link uses Ethernet for both layer 1 and layer 2 functions. That means the link uses the same familiar Ethernet header and trailer, as shown in the middle of the figure, of the following figure. Here we have Ethernet header and Ethernet trailer. R1 will remove this Ethernet header and trailer and re-encapsulate another header, Ethernet header and trailer, with source R1 Giga01 MAC address of this, the MAC address of this interface, and the destination MAC is the MAC address of this of R2 Giga0/0 MAC address. R2 will remove this Ethernet header and trailer and re-encapsulate another header, Ethernet header and trailer, and forward the packet to PC2. There is a note here. The figure shows a small cloud over the Ethernet link as a way to tell us that the link is an Ethernet WAN link rather than an Ethernet LAN link. We have a cloud here just to tell you that this is an Ethernet WAN link, not an Ethernet LAN link. So the second topic of this discussion will be about IP routing. Now we give a fundamental concept about WANs, and now we will discuss the IP routing. Of course, the IP routing, we will discuss which layer? Layer number 3, of course, the network layer. So at the network layer of TCP/IP, two options exist for the main protocol around which all other layer functions revolve. What are these two options? Internet Protocol version 4 and Internet Protocol version 6. So the network layer of the TCP/IP has only two options, IPv4 and IPv6. Both IPv4 and IPv6 define the same kinds of network layer functions, but with different details. The Internet Protocol focuses on the job of routing data in the form of packets, because as we know, we call it packets from the layer 3 point of view. Of course, from the source host to the destination host. IP doesn't concern itself with the physical transmission of data. Instead, it relies on the lower TCP/IP layers to do the physical transmission of data through the data link layer and the physical layer, who are layer 1, which are layer 1 and layer 2. Instead, IP concerns itself with logical details rather than the physical details of delivering data. In particular, the network layer specifies how packets travel end-to-end over a TCP/IP network, even when the packet crosses many different types of LAN and WANs. So, if we have a host here and a host here, IP itself concerns itself with the logical details, regardless of we are connecting through an Ethernet here or a leased line here or an Ethernet over MPLS WAN. Regardless of the physical details, it concerns itself on how to send the packet end to end over the TCP/IP network, even if the packet is crosses across different LAN and WAN links. So let's define three definitions for these three things: the IP, the IP addressing, and the IP routing protocol. What is IP or Internet Protocol? It defines what it means to route an IP packet from sending host to destination host while using successive data link protocols. What is IP addressing? It gives the rules that help to make IP routing much more efficient by grouping addresses into subnets. And we will know later what are subnets. IP routing protocols gives routers a means by which to learn routes to all the IP subnets in an internetwork. So IP defines how to route the IP packet from the sending host to the destination host. What it means to route an IP packet from sending host to destination host. IP addressing gives the rules to make IP routing much more efficient by grouping hosts or addresses into subnets or networks. And we will know later what are the difference between networks and subnets. Subnets is some kind of networks. And what is subnetting? We will know this in a later video. So we will not deep dive here, just to know that IP addressing groups addresses into subnets. And the IP routing protocols gives the router means to learn the routes and to send packets to all IP subnets if you need. And there are different types of IP routing protocols. And there are different types of IPs. We have here version 4 and IP version 6. And for the routing protocols, we have REP, we have OSPF, just for your information. And there are chapters for each one of these routing protocols. We are giving here fundamentals. So we also have EIGRP, we have intermediate system, and we have BGP as an examples of the routing protocols. So here let's think about how the network layer route or forward packets. Routers and end-user computers, often called hosts, work together to perform IP routing. The host operating system has TCP/IP software, including the software that implements the network layer. Hosts, or we call PCs, mobile phones, smartphones, laptops, all of these are called hosts, use that software to choose where to send IP packets, often to a nearby router if the destination is in another LAN or another subnet. Those routers make choices of where to send the IP packet next. Together, the hosts and the routers deliver the IP packet to the correct destination. And we will see how the hosts and routers work together to deliver the packet successfully from the source to the destination. Let's give an example here where PC1 needs to communicate to PC2, where PC1 is on LAN 1 and PC2 is on LAN 2. First of all, PC1 PC1 has an IP address 150.150.1.10 and PC2 has 150.150.4.10. They are in different subnets. and this is the subnet address. But just for your information, later we will deep dive on this addressing. BC1 realized that the destination, which is BC2, is in another subnet or another group. So it has to send the IP packet to its default gateway or default router, which is R1. And BC1 is configured with this information. It has the IP address of its default gateway. If you are using Windows, you can think about the TCP IP configuration and find it, and you will be asked to define the IP address, the subnet mask, and the default gateway. But for now, you have to know that BC1 sends any IP packets that is destined to another host, not in the same group or in another group. When R1 receives that packet, it checks its IP routing table. And this IP routing table is built by using an IP routing protocol or configured statically. But don't think about this right now. Think about the logic how the network layer routes the packet. R1 checks its IP routing table and decides to send the packet to R2 over the serial link and out of its serial 0 interface. Now R2 receives the packet, and of course it do the de-encapsulation and re-encapsulation process, as we mentioned in the previous slides when we were discussing WANs. R2 will receive the IP packet. After here it will remove the Ethernet header and trailer and re-encapsulate a new HDLC frame header and trailer before sending to R2. But it determines from each interface based on the IP routing table. Now R2 received the frame. It de-encapsulates the Ethernet header and trailer and re-encapsulate another header and trailer, Ethernet header and trailer. But before that, it checks its IP routing table and decides to send the frame or the IP packet out of fast Ethernet 00 destined to R3. This process is called routing. R1 decides to send to R2, R2 decides to send to R3, and R3 eventually will send to BC2 out of Giga 0/0. And after de-encapsulating the Ethernet header and trailer and re-encapsulate a new header and trailer. Let's define what is path selection. It refers to the routing process shown in the previous figure, and at other times it refers to routing protocols. Each routing protocol, when we discuss later what are the routing protocols, and we will take each one of them, we will find out that there is something called path selection. If you have a path or a different paths, which path you can choose. Sometimes the routing protocol chooses a path, and you can influence the routing protocol to choose another path. This is called path selection. So it refers to routing protocols, specifically how routing protocols select the best route among the competing routes to the same destination. Sorry. There is a note here. The default router is also referred to as the default gateway. So sometimes we call it default router, and sometimes we call it the default gateway, which means the router inside the LAN that can take IP packets that is destined to another host in a different group. How network layer routing uses LANs and WANs. While the network layer routing logic ignores the physical transmission details, the bits still have to be transmitted. To do that work, the network layer logic in a host or router must hand off the packet to the data link layer protocols, which in turn ask the physical layer to actually send the data. This is when we describe the functions of the TCP/IP model layers. We have here layer 3. It gives the IP packet to layer 2. It gives the layer 2 packet to the physical layer to send the data. So the network layer logic in a host or router must hand off the packet to the data link layer protocols, which in turn ask the physical layer to actually send the data. The data link layer adds the appropriate header and trailer to the packet, creating a frame before sending the frames over physical network. Actually, the routing process forwards the network layer packet from end to end through the network, while each data link frame only takes a smaller part of the trip. As we mentioned before, we have a host here and host here. The IP packet remains, this is the IP packet, remains intact from the source to the destination. So it is end to end, it exists the same. But the Ethernet frame keeps changing over the path. Sometimes you remove it and add a new one, and then removes the new one and add another new one. Each successive data link layer frame moves the packet to the next device that thinks about network layer logic. So in short, the network layer thinks about the bigger view of the goal, like send this packet to the specified next router or hosts, while the data link layer think about the specifics, like encapsulate the packet in a data link frame and transmit it. This is how layer 3 works with the data link layer protocols. Let's give an example here. So we have here PC1 and PC2. PC1 is trying to communicate to PC2. So first of all, PC1 do some mathematical equation or something to determine whether the destination host is in the same group or in a different group. So in this example, PC1 will find out that PC2 is in a different group, so it has to send the IP packet to the default gateway, which is R1. PC1, before sending the IP packet, it encapsulates an Ethernet frame, header and trailer, and send to R1, which IP address R1, this interface on R1 has an IP address 150.150.1.4. And as you can see here, the first 3 octets are the same, which means they are in the same subnet or in the same group. But don't think about this right now, because we will discuss it in more details in later videos. Now, PC1 encapsulated the frame and sent the frame to R1. R1 will check its IP routing table and has a subnet check the destination IP address. This is the destination IP address in the IP packet and find a matching entry for this subnet inside its IP routing table. Once it finds an entry, the entry has another fields or another places where it defines which outgoing interface should the router send the frame out of. And in this example, we have serial 0, and the next hop IP will be 150.150.2.7. Once R1 decides from which interface it will send the frame, the IP packet, it will check the WAN protocol used here in this interface. Let's assume we are using leased line and layer 2 protocol HDLC. So R1 have to re-encapsulate a new HDLC header and trailer before sending the frame out of serial 0. Now R2 received the frame, the HDLC frame, out from this interface. First, it removes the HDLC header and trailer and check the IP packet's destination IP address, compares the destination IP address to the routing table, find the matching entry, send out of this interface to this next hop, which is R3. So R2 re-encapsulate a new Ethernet header and trailer because the WAN technology used here is an Ethernet over MPLS, which is an Ethernet WAN. So that's why we are adding a new Ethernet header and trailer, and based on the IP routing table of R2, the outgoing interface will be fast Ethernet 00 destined to R3, which is 150.150.3.1. So R2 send to R3 the Ethernet frame. Once R3 receives the Ethernet frame, it will de-encapsulate the header and trailer and compare the destination IP address to its routing table. Similarly, find a matching entry, send out of this interface, and next hop is available means that the destination is in the same network. So R3 will de-encapsulate and re-encapsulate a new Ethernet header and trailer and send out of giga/0/0 destined to PC2, and PC2 receives the IP packet or the frame successfully. This is how the network layer uses LANs and WANs. Let's discuss something about the IP routing process, which is Internet Protocol addresses or IP addresses and subnetting, just fundamentals. IP defines network layer addresses that identify any host or router interface. Remember this. Any host should have an IP address. Any router interface should have an IP address. So if a router has 3 interfaces, each interface must have an IP address that connects to a TCP/IP network. The idea basically works like a postal address. Any interface that expects to receive IP packets needs an IP address, just like you need a postal address before receiving mail from the postal service. TCP/IP groups IP addresses together so that IP addresses used on the same physical network are part of the same group. IP call these address groups an IP network or an IP subnet. Let's think that we have here hosts and here is a switch. We have PC1 and PC2. PC1 starts with 10.1 10.1.1 and BC2 is 10.1.1.2. Subnetting determines which octets defines the group. It can be these 2 bits, it can be this 1 byte, I mean this octet, or it can be these 3 octets. But if they are the same, let's assume that the subnet ID or the subnet number is coming from the first 3 octets. If they are the same, then these 2 hosts are in the same group or the same subnet or the same network. Let's assume we have here another switch in another LAN, and PC2 and PC3, sorry, has an IP address of 10.2.1.1, and the subnet consists of the first 3 octets. So if you will compare this to this, you will find that they are in 2 different subnets or 2 different groups or 2 different networks. This is subnetting. But there are more details how to subnet a class A IP address or class B or class C and so on. And this has a specific chapter, and we will make a specific video for this demonstration. What is IP routing or Internet Protocol routing? From the perspective of IP routing, the grouping of IP addresses means that the routing table can be much smaller. Why? Because a router can list one routing table entry for each IP network or subnet instead of one entry for every single IP address. What this means? If we have a router here connected to a switch, and this switch has PC1, BC2, BC3, and BC100. They are all in the same group. Using IP routing, R1 will have one entry in its IP routing table for this all group, not an IP address for each one of these. So instead of having 100 entries, R1 will have only one entry that represents this group. 2 IP addresses not separated from each other by a router must be in the same group or subnet. For now. No, not for now, but for all the time. Because later on when we will discuss VLANs, VLANs should be separated by a multi-layer switch or a layer 3 device like a multi-layer switch or router. So 2 IP addresses not separated from each other by a router must be in the same group or subnet. 2 IP addresses separated from each other by at least one router must be in different groups. Why? Because if these 2, let's have a switch here and a PC here. If this PC is in the same network as this group, when R1 will receive, first of all, R1 will not receive that frame because PC1 will find out that the destination is in the same group, so it will not send it to the default gateway. So it will think about that the destination is in the same group, but it is not. So it will never ever reach this PC. That's why even if the router received this frame, and it will have a duplicate entries, and this router will not allow you to give 2 interfaces the same IP address. This is from the basics. What is the IP header of the network layer 3 packet? First of all, you have to think about, for now, for only the source IP address and the destination IP address. And in IPv4, they are 32 bits. And by the way, this is the IPv4 header. We will not discuss the IPv6 header, which is the source IP address will be 128 bits. But for now, we will discuss only IPv4 packet header. And this version determines whether we are using an IPv4 or an IPv6 in the source and destination addresses. So you have to think about only the source and destination IP addresses in the packet header for now. The other fields do some other things, but later on you will know, like the DS field do some quality of service, but don't think about this now. Just think about the IP header contains the source IP address and the destination IP address, and each one is a 4 bytes or 32 bits. What is the IP routing protocols? What it does? For routing logic to work on both hosts and routers, each host and router needs to know something about the TCP/IP network. Hosts need to know the IP address of their default router so that hosts can send packets to the remote destinations. Routers need to know routes so they forward packets to each and every reachable IP network and IP subnet. The best method for routers to know all useful routes is to configure the routers to use the same routing or the same IP routing protocol. So routers learn routes through routing protocols. Hosts need to know the IP address of the default gateway before sending packets to remote destinations. Alternatively, instead of using routing protocols, a network engineer could configure or type all the required routes on every router, which is something difficult to do, but it's available to be accomplished. However, if you enable the same routing protocol on all the routers in a TCP/IP network with the correct settings, the routers will send routing protocol messages to each other. As a result, all the routers will learn routes for all the IP networks and subnets in the TCP/IP internetwork. Let's give an example. First of all, IP supports a small number of different IP routing protocols, as we mentioned, RIP, OSPF, EIGRP, intermediate system, and BGP. So IP supports a small number of different IP routing protocols. However, many routing protocols uses the same general steps for learning routes. Each of them do these 3 steps. First step, each router independent of the routing protocol adds a route to its routing table for each subnet directly connected to the router. If a router here is connected to a switch and the switch is connected to a host here, this interface has an IP address that resides inside an IP group or IP subnet. So independent of the routing protocol, the router adds a route to its routing table for each of these direct subnets. If it has another switch here in another subnet group with another PC here, this interface is in another subnet. So it will have 2 routes as connected routes in its routing table. Each router's routing protocol tells its neighbors about the routes in its routing table, including the directly connected routes, and routes learned from other routers. After learning a new route from a neighbor, the router's routing protocol adds a route to its IP routing table, with the next hop router of that route typically being the neighbor from which the route was learned. Let's give an example. BCR3 here has a connected entry for the subnet 150.150.4.0. This is a connected route. R3 advertise this route to the neighboring router through a routing protocol. This is step number 2. R2 then step 1, R3 is in a subnet that is 150.150.4.0. It adds this subnet to the routing table, then advertise this route to the neighboring router through or via a routing protocol or statically configured routes as an alternative. R2 do the same. It learns the subnet and adds it to the IP routing table, and then advertise this subnet to the neighboring router, which is R1. R1 do the same thing. It adds the information or the subnet to the IP routing table and learn it through this serial interface and from this neighbor as a next hop, which is R2. So when PC1 needs to communicate to PC2, now R1 has a route or a subnet to this destination. So when PC1 wants to communicate to PC2, it sends to the router, the default gateway R1. R1 check the IP routing table. Yes, it has an entry learned from R2. It's sent to R2. R2 has an entry for this destination subnet and learn it from R3, so it decides to send to R3 and so on. Also note that at the final step, routers may have to choose between multiple routes to reach a single subnet. If we have another router here connected to R1 and this is connected to R3. So we have a route here to reach PC2 and a route here to reach PC2. When that happens, routers place the best currently available route to reach a subnet based on a measurement called a metric. So this route or this path has a metric and this path has another metric, and the best one of them will be chosen to be added into the routing table. Let's discuss something called domain name system or DNS. TCP/IP defines a way to use host names to identify other computers. Here we said BC1, not 150.150.1.1 for simplicity. But actually, the network uses the IP address, so we don't have to remember all the IP addresses of the hosts. Instead, we use host names to identify other computers. The user either never thinks about the other computer or refers to the other computer by name. Then, protocols dynamically discover all the necessary information to allow communication based on that name. Let's give an example. When you open a web browser and type in the host name www.google.com, Your computer does not send an IP packet with the destination IP address of www.google.com. It sends an IP packet to an IP address used by the web server for Google. TCP/IP needs a way to let a computer find the IP address used by the listed host name, and that method uses the domain name system. Let's give an example. PC11 want to communicate with server 1. First of all, PC11, when you open the browser, by the way, server 1 is a web server for this example, and PC11 you will type in the browser www. For example, google.com. The first thing will happen, PC11 will send to the DNS configured in its TCP/IP configuration, because in PC11 or any host, the TCP/IP configuration are first the IP address, second the subnet mask, and we will know later why the subnet masks. Third, the default gateway or the default router that PC1 will use when sending to another host in a different group or subnet, default router or default gateway. Fourth, the DNS IP. So PC11 will communicate to the DNS server configured in its TCP/IP configuration, asking what is the IP address of server 1. DNS servers have a database for all host names and the corresponding IP addresses. So this query will be used by the DNS server and check its database and find the IP address of server 1 and send the response, a DNS reply, giving the IP address of server 1. Now PC11 know the IP address, and then it will communicate and send the IP packet with this destination IP address in the IP packet. Finally, DNS defines much more than just a few messages. DNS defines protocols as well as standards for the text names used through the world and the worldwide set of distributed DNS servers. This worldwide set of distributed DNS servers, we call them root hints. These root hints are 13 worldwide DNS server. Or I think they increased the number, but for my knowledge, I know that they are 13 DNS servers.
Have a new mail.
The domain names that people use every day when web browsing, which look like www.example.com, follow the DNS naming standards. Also, no single DNS server knows all the names and matching IP addresses, but the information is distributed across many DNS servers. So, the DNS servers of the world work together, forwarding queries to each other until the server that knows the answer supplies the desired IP address. What this means, if you have a host name like www.google.com, some servers are responsible for this .com, some servers are responsible for .net, some servers are responsible for .edu, and so on. So the DNS servers work together until this complete host name will be resolved by one of them. Another thing you have to do, the address resolution protocol. Actually, we used it without you feel in the previous examples, but we didn't mention it because IP routing logic requires that hosts and routers encapsulate IP packet inside data link layer frames. For Ethernet interfaces, how does a router know what MAC address to use for the destination? Of course, it doesn't know, but through ARP or Address Resolution Protocol, it can know the destination MAC address. On Ethernet LANs, whenever a host or router needs to encapsulate an IP packet in a new Ethernet frame, the host or router knows all the important facts to build that header, except for the destination MAC address. So the sending host knows the IP address of the next device or the destination IP address. It also knows the source IP address because it is the sending host. So it has an IP address. When filling the IP packet header, we said we have source IP and destination IP. So the sending host knows this source IP because it's its own IP. And it knows the destination IP because this is the IP address it needs to communicate with. It knows the source MAC of the sending device because it's its own MAC address. But it still don't know or doesn't know the MAC address, the destination MAC address of the destination host. So this is missing. It knows all these three information and doesn't know this. So using ARP, it will know the destination MAC address so it can build that header and send a frame. So TCP/IP defines the address resolution protocol as the method by which any host or router on a LAN can dynamically learn the MAC address of another host or router on the same LAN. ARP defines a protocol that includes the ARP request, which is a message that makes the simple request. If this is your IP address, please reply with your MAC address. Simply, because I don't know the destination MAC address, I send an ARP request asking if this is your IP address, please give me your MAC address so I can use it as a destination MAC address in the Ethernet header. Also, ARP defines the ARP reply message, which indeed lists both the original IP address and the matching MAC address. Let's give an example here where R3 is trying to send an IP packet to BC2. First of all, R3 knows the destination IP, but it doesn't know the destination MAC. So switches in the Ethernet LAN can forward the packet the frame based on. So first, R3 will send an ARP request, and this ARP request is broadcast. And we will mention why. We mentioned earlier in the second video, chapter 2, what is the difference between broadcast and unicast. Broadcast is something sent to all hosts in the same group. Why R3 sends the ARP request in broadcast? Because switches relies on the destination MAC, and R3 doesn't know the MAC address. So switches should forward all this frame to all hosts in the same group. That's why the ARP request is broadcast. Now when the switch receives this request, because the destination MAC address will be inside the ARP request f.ffff.ffff.fff, which is a broadcast frame. This ARP request will contains this information: the sender IP address, R3 IP address, the sender MAC, this interface MAC address, the target or destination IP address of R4 of PC2, but this information is missing, the target or destination MAC address. So when PC2 receives this broadcast request, ARP request, because its IP address is listed in the destination IP, it will send a reply, ARP reply, giving its MAC address to this R3. And this ARP reply is unicast. Why? Because the information are complete. The target IP is R3 IP address. The destination MAC or the target MAC is R3's MAC address, this interface. The sender IP is PC2 IP address. The sender MAC is PC2 MAC address. So this frame is a unicast ARP reply. Now R3 gets the MAC address of PC2. Now it can encapsulate an Ethernet header and trailer. This is the header and trailer, and the header contains the source MAC of R3's interface, and it contains the destination MAC learned through ARP, and R3 can send this frame to PC2 as a unicast, and switches in between can take decision based on the destination MAC. Note that hosts and routers remember the ARP results, keeping the information in their ARP cache or ARP table. So there is something called ARP table or ARP cache exists in hosts and routers. A host or router only needs to use ARP occasionally to build the ARP cache the first time. Each time a host or router needs to send a packet encapsulated in an Ethernet frame, it first checks its ARP cache for the correct IP address and matching MAC address. Hosts and routers will let ARP cache entries time out to clean up the table, so occasional ARP requests can be seen. There is an important note here. You can see the contents of the ARP cache on most PC operating systems by using the ARP-A command from a command prompt. Let's give an example here and type this command. Let's first exit this presentation. One moment, discard. Let's press Windows and R on the keyboard. Type CMD to open the command prompt. Type ARP-A. This will give you the contents of the ARP cache. So press enter, and as you can see, all the IP addresses and the corresponding MAC address. This, for example, my router or my default gateway, and this is the MAC address of the default gateway. So when my computer or my host or my PC needs to send to outside hosts as a destination, it will not send an ARP request because it has in its cache the destination MAC. Let's resume the presentation and the demonstration. Last thing we want to discuss here is something called, let's bring the pen, ICMP echo and the ping command. This is a very important tool that you are going to use all your time during your work as a network engineer. After you have implemented a TCP/IP internetwork, You need a way to test basic IP connectivity without relying on any applications to be working. The primary tool for testing basic network connectivity is the ping command. Ping means Packet Internet Grouper, uses the Internet Control Message Protocol or ICMP, sending a message called an ICMP echo request to another IP address. The computer with that IP address should reply with an ICMP echo reply. If the sending host who sent the ICMP echo request does not receives an ICMP echo reply, it means the destination is not reachable. If that works fine, it received an ICMP echo reply, you successfully have tested the IP network. In other words, you know that the network can deliver a packet from one host to the other and back. ICMP does not rely on any application, so it really just tests basic IP connectivity, layer 1, 2, and 3 of the OSI model. Let's assume we have here PC1, who is called Hannah, and it wants to test the connectivity between itself and PC2 with a host name Harold. You can ping Harold from Hannah. First, you will ask the DNS, as we mentioned, because the ping, the Hannah will not use the host name, it will use the IP address. So first, you will ask a DNS to get the IP address of Harold, and then the ICMP echo request will be sent from Hannah to Harold, using the IP addresses of Hannah as source and Harold as destination. If Harold can reply and the packet is delivered successfully to the ICMP echo request delivered successfully to Harold, Harold will reply using an ICMP echo reply. Then it means the connectivity between the two hosts is correct and successful. If you want to check the ping command, let me discard. Open the command prompt similarly as we did with the ARP cache. Type simply ping and the destination that you are wanting to test with. Let's give an example with www.google.com. As you can see, 4 packets are sent and you got 4 replies back. So the sent equal 4 packets, the received equal 4. There is nothing lost. If there is something lost, it means that there is a network issue. If the lost is 4, it means that you will not get a reply, you will get a request timeout. So to this, we come to the end of the presentation. I hope it's been informative and wish to see you next in another videos and another CCNA chapters. Thanks for watching.